programming of the robots, that how the robots are programmed. So robotic programming is the process of defining specific commands of an application for industrial robots to automate. So firstly, application instructions are inputted to the robot control system, and after that it interprets the steps and then relays the information in the robot's programming language to the PLC or microcontroller of the industrial robot. So the robot PLC or microcontroller then moves the robot's actuator or motor, which controls the robot axis and according to their commands of the programmed application. So without programming, industrial robots would not be able to automate production-related tasks. Regardless of their application type, all the robots need to be programmed prior to implementation of an automated manufacturing system. So various types of coding languages are used to program the industrial robots. These are C, C++, C-, Java, MATLAB, Pascal, and Python. Safety considerations which includes in the industrial robots. So firstly, there are some hazardous areas of this robot. So manual or physical access to areas which are hazardous. Second thing is hazards which arise from faulty behavior or the part of the system in the industrial robot, and some injuries which is caused by the peripheral equipment which are faulty. So, but there are some following safety conditions which are applicable by using this robot. So, first is the manual or physical access to areas which are hazardous, and the second is peripheral equipment must not represent a hazard to the programmer or the other person. The next thing is the future of robotics, that how this industry is growing, and nowadays we can see in manufacturing industries, also in the medical field, they are used. You can see rise from 2010 to 2020, where it is going from 1.06 million to 3.02 million industries. So successfully application of industrial robots, their reliability and availability, and the active implementation of the Industry 4.0 concept has stimulated growing interest in robots optimization. As the following chart you can see, which is based on the data from the International Robotics Federation, shows the operational stock of industrial robots has tripled over the past decade, with more than 3 million robots in use across various industries by the end of 2020. According to the IFR, Asia leads the way in the shift to automate processes, with China in particular installing industrial robots at a breakneck speed. In 2020, China installed 168 and 400 industrial robots, amounting to 44% of global installations. So you can see that how this industry is growing. So now let me show you the application of this industrial robot. And for this, I am writing the forward kinematics code. And forward kinematics is defined as where you give the joint angle value and then it gives the end effector position. So you have seen that these type of components are very important. Let me show you here. So you see, this is the 4 degree of freedom star robot. You can see here the first joint, second joint, and the third joint as well moving in rotation. And the last one, which is a prismatic, is moving in upward and downward direction. So we have to find that how these joint angles are moving in which degrees, and then after how in what position this end effector is. So for this, let me show you that. This figure, for that I am writing this forward kinematics code. So this is the first joint, this is the second joint, and this is the last one joint. First and second joint are the rotational joint, and the last one is the prismatic joint. You can see, as I told you, that the length of the link is defined by measurement of distance in acceleration with first joint to the second joint. So this is L1 and this is the L2. This is the link offset. So the measurement of distance in z direction between the two joints. So this is known as the link offset. So you see that Firstly, I have defined Q1 and Q2 as joint angles in radians. D1 and D3 are the link offsets, and A1 and A2 are the link lengths. So I give input as the Q1 and Q2 and D3 because the rotation in Q is in Q1, Q2, and for the last one, prismatic joint. So you see, for example, I have taken some value. A1 is the 0.165, A2 is the 0.118, and D1 is the 0.116, and all these values are in meters. So you see that this is a transformation matrix which is written for each joint angle and for each joint also. So here this is the link for the dx parameter for the link 1, this is for the link 2, and this is for the link 3, and I have named it as SCARA robot. After that, I multiply all these transformation matrix together and it gives me output with the homogeneous transformation matrix. And after that, the limit I have decided for the first joint is minus 99.67 to the plus 99.67, and for the joint 2, this is minus 112.335 to plus 112.335, and for the last one, which is a prismatic joint, so it can only move in upward and downward. So here I define it as 0 to 0.116. So when I run this code, you can see that it asks me for some values of joint angle. So firstly, let me give this 0. For the second joint, also 0, and for the third joint, this is 0. And now I enter this show me and effector position. That firstly it is in 0.2830 at 0 and 0.160, and you see that this is the original position of this robot C. But after that, when I give it the new value, like a 90 degree, and the maximum value, or let me just 0.005. So you see that now it gives me a different value, minus 0.1180 in X direction, 0.1650 in Y direction, and 0.1610 in Z direction. You see now robot has changed its position. Firstly it was linear, but now it has moved by 90 degrees. So you can take a guess at how this robot works in different environment and how you can move the robot with giving this joint angle value. And also this graph shows the whole range from -1 to 1 for X and Y position of this robot. So this is all from my side. Thank you so much. Now you can post your queries if you have any, so that I'll try my best to answer your queries. Thank you so much.